Hello, and welcome to Parallel Computing with Dask. I'm Dhavide Aruliah. This course is about the Python library Dask that helps data scientists scale their analyses painlessly. First, let's ask what big data means. Roughly speaking, it's more data than a single machine can accommodate. To understand that precisely, we need to discuss computer storage. Let's clarify storage units. In conventional metric units, prefixes like kilo, mega, giga, and tera denote factors of 1,000. For instance, kiloWatt, megaWatt, gigaWatt, and teraWatt mean 10 to the 3, 10 to the 6, 10 to the 9, and 10 to the 12 watts respectively. Computers, however, use binary or base 2 notation, not base 10. The base unit of data storage is the binary digit or the bit. 8 bits make 1 byte of data. So with data, it's conventional to use kilo, mega, giga, and tera to scale units up by 2 to the power 10, or 1024, because that's almost 1,000. Then a kilobyte is 2 to the 10 bytes, a megabyte is 2 to the 20 bytes, a gigabyte is 2 to the 30 bytes, and so on. Hard disks, then, are used for permanent storage. Current hard disks can accommodate terabytes of data, but require milliseconds to access data. Computers use RAM, or random access memory, for temporary storage. Data in RAM vanishes when it's shut down. Data in RAM can be retrieved in nanoseconds to microseconds, but the largest RAM configurations are a handful of gigabytes at best today. So this table, modified from a table by Brendan Gregg, tells the story. These are approximate data transfer times from RAM, from hard disks, and from the internet, say a trip from San Francisco to New York. What matters is the relative timescales, nanoseconds to microseconds to milliseconds. If we pretend transfer from RAM takes 1 second, then transfer from solid-state disk takes 7 to 21 minutes. Transfer from a rotational hard disk takes 2.5 hours to a full day, and transfer from the internet takes almost 4 days. This is what big data really means. When data overflows from RAM to the hard disk or to the cloud, the relative processing time effectively jumps from seconds to minutes or days. With that in mind, let's examine memory usage on my laptop. We need tools from the psutil and the OS Python modules, so we import those. We then define a custom function memory footprint to return how much memory the Python process uses. We don't have to understand its inner node workings, but notice that the result returned is rescaled from bytes to megabytes. We import NumPy and call memory footprint before doing any work. We then create a NumPy array X that requires 50 megabytes of storage, and then call memory footprint again to see the memory usage afterward. Sure enough, the process pulled roughly another 50 megabytes from the operating system in order to create X. We next compute X squared and again compute the memory usage before and after. We find an additional 50 megabytes of RAM is acquired for this computation, even though the computed result isn't actually bound to an identifier. We can use the NumPy array's nBytes attribute to find out its actual memory requirements. The result is given in bytes, so dividing by 1024 squared gives the size in megabytes, a more readable number. We can also create a pandas DataFrame df that is based on X. The DataFrame has an attribute memory usage that returns an integer series that summarizes its memory footprint in bytes. As before, we can divide by 1024 squared to get the memory footprint in megabytes. So before we dive into Dask, try some exercises now to make sure you know how much memory you're using.